let me just, I've got some water on the front of my spectacles, aka, oh, and look, I've just put my glass in front of the camera like a true professional. There we go. So let's just crack in. There's one or more ways to create a custom structure in Haskell. Let's see what that is and how it differs from others. Okay, new type is a way to create a lightweight wrapper around an existing type. Unlike type aliases, let's quickly refer. A type alias would be type poop. Hold on. Equals int. Okay, that's a type alias. You're just you're referring to int and giving it the name poop. So that's an alias. New types make an entirely new type for the compiler from the compiler's point of view, as the name suggests. However, such data types don't have additional runtime overhead, which means that it would work as fast as the underlying type without the wrapper. Okay, let me just quickly change some of this business here. Yeah, you go there, you go there, you hide over here. Cool, got it. So let's go into it. You can declare a data type as a new type only if it has an exactly one constructor. So when I did data equals like this, for example, you can't do a new type if it's going to do string. Actually, well, it'd have to be, but yeah, you can't do something with a sum type. That's what they're called. So you can't do that. It literally can only work with one value. So let's have a look. One constructor with exactly one field. It is a compiler error if you try to define a new type with another number of constructors or fields. The syntax is similar to defining an ordinary data type, but you use the new type keyword instead of the data keyword. New type is a product type. Oh, okay. So much like products, here we go. Here's an example. Sometimes I just like to see like that. It's good to see a little bit of colour, isn't it? Except my IDE does that madness. Thanks. Which is just what we need. Here we go. So we've got a new type of attack, and its constructor is make attack, and that's an int. Okay. So that's a product type. Let's see what else it says. The same rule about name fields as for any data type applies to new types as well, meaning you can write the above type as follows. So you can write it like this. But if we remember, it does say here, has exactly one constructor with exactly one field. So my thinking would be, let's try and see if we can make the compiler tell us that we're doing wrong. So we're going to do attack. Okay, and that's going to be a p of a type int. And let's see if it isn't. Well, first let's make it compile. Let me just do like that. I'm going to restart it just to double check. Oh look, we get to see the output. Probably not what we want. I'll get rid of that. Yeah, goodbye. Okay, and then hopefully if we do yes, now it's not happy. So the constructor of new type must have exactly one field. Okay, so we just proved that to ourselves for good measure. You can use the mattack constructor to create values of the attack type, and you can pattern match on make attack, so this one, as on ordinary data types. Okay, when using new types, you pay an extra development cost of writing extra wrappers and unwrappers, but at the same time you get additional compile time guarantees of not mixing types. Okay, is there like an example of what I'm trying to say? Nope. So new types serve the purpose of creating safer and more maintainable interfaces. Let's prove that. Okay, let's prove it. So say we have a function to get a BMI. Aha, yeah. This is going to demonstrate some good little examples. Let's go like this. Oops. Which way around? I'm going like that. Yeah, here we go. So this is why new types and things like that are useful. We'll see right now. So we've got my BMI, and it takes a double, and returns a double. But the problem is when you see that on the first off, well, which double's this, and what are the doubles to do with? There's no indication from, without looking inside the function. Well, here you can see height and weight, which is fine. But then when you're using it somewhere else, when you call my BMI, what does it actually, what is it? You don't know. All you know is if you sort of hover over it, you get a representation saying, oh, well, this is a double. And you're like, oh, cool, thanks. Well, which way round is it? That's the problem with it. So we'll remove that for a moment. And I can use it to calculate my BMI. So my BMI, 270. Imagine how terrifying it would be if one accidentally messes with the order of the height and weight. Yeah. So for some reason, these were to be flipped and someone was like, no, actually I want the first one to be weight and the second one to be height. Well, because you're using double, there's no actual indication that that's happening. You're just using double. So if that's mixed, then you get totally the wrong answer. Yet, if we keep it with double, it's going to compile, isn't it? Because you are ineffective. Effectively, you are passing double, which is what it requires. But you're not being explicit enough, or you're not giving yourself enough clues as that's what you're trying to do. So my BMI, this is what you can now do. So my BMI, you can give it a height, a new type of height, and a new type of weight, and then that returns a double. So it's fine to return a double. I mean, even you could if you wanted, you could be even stricter and just that double type could be BMI. But now, because we've got a height and a weight, you can't, you've got a good indication when you look at your types. If you get an output that's like really weird, you can look at the types and go, oh, okay, so the first one's a height, I get you. But there's even more of a reasoning is like this. Look, you have to wrap them. Shall we quickly... oh no, I guess it'll come in a task. But this is the key right here. So you can, because we're using a constructor, which is, where is it? That part. So that was called make attack, but for our scenario, it's called height. Oh, sorry, I should be using that. It's called height. So my BMI, oh no, we've not even made it. But yes, it's a height and a weight, which are both new types. And then to use them, so for an example, it looks something like this. It'd be new type, and it'd be height. And then you could just height, and that would be double. Double. Yep. I think I've got that right, haven't I? Just double checking. Yes, that's cool. So you could have it like that. And then what that allows you, basically this types are also functions. So this, in essence, if you look at the type of this, especially if you spell, it'll be a height that expects a value, returns you a double. So you have to, height expects a value and it returns you this height here. So to get it to work, well, actually we can show it like height. Or should we just call it height make? Like that. And then you'd have to call it like this. Okay, because these can be the same names, but they are different things. Okay, so you have to call it like that. So you're saying, pass me 200, and I'm going to go into here, and then I'm definitely now a height. And then the type would be like this. So if we were to do this, ignore the GHTI part of it. Yeah, so if we look at it, that'd be height, because that's of that type. Here, of that height. And then weight, actually that'd be, there we go, yeah. So you see what's happening? So we're literally, you can't pass my BMI any random doubles because you have to wrap them inside this new type that we've created. So this new type here. So we have to wrap it in that. Because if we don't wrap it in that, then it doesn't know, if we were just to pass it 200, it's going to go, no, You've given me a double. I expected a height. Okay. So that's what's happening there. And I think they're going to get us to work through it with an exercise. So improve the following code, type definition and function implementations by introducing extra new types. Okay, so hint, if you complete this task properly, you don't need to change the implementation of hitPlayer function at all. Where's hitPlayer? There's hitPlayer. Okay, so hitPlayer expects, so they want us to use new types. Player health, player armor, player attack, player strength. So the problems are here. So ideally, so what do they want? Don't change the implementation. Improve the following code, type different function by introducing extra new types. Oh, so we're just literally going to create new types. So we'll have to create new types for all of them. That's what it'll be. So it'll be new type. And we'll call it player. Oh, hold on. Is there player armor already? Oh, okay. Well, let's try it. Player. See, this is what. Oh, okay. Can you see what the issue is? I've just put it as a lowercase. It was looking for the function. I was like, hold on. How's it? What? Yeah, that makes sense. That's going to be an int. Okay. And then we'll just copy those. 1, 2, 3, 4, 5. Yeah, there we go. So player armor. Second one's going to be, well, first one will be health. Yep. And that'd be health also. Cool. Armor, we've done attack. Attack. Oh, Mr. C. Oh, CK. Yeah, that's why it went back. Okay, and then we've got dexterity. So dex. Oh, I can hear my cat. So she's probably going to meow because that's what cats do, don't they? They go meow. Unless I make that noise like that, and then she'll probably. Oh, thanks, Savvy lad. Thanks for raiding. I think that's what it is. Yeah, it's not quite sinking in. I don't think, but we'll soon find out. So we're going through this exercise here. Strength, player strength. Yep, and then we'll do it same here. So we'll just create new types, and then ideally it should just compile, but it won't because we've got to sort of update all these, and then we'll get a bunch of errors, which is exactly what we want. This one, yeah, this one, yeah, this one. So the idea here is we're making, because if you look at these functions, they're all expecting ints, which is pretty damn useless because that's what all of these were before. And we're creating new types to help with that. So you check your stats. Oh, I'm interested now. I have 262 hours streamed. Oh, God. That's amazing. That's a lot of hours, dude. Where does it tell you? Oh, does it tell you on the? Oh yeah, it'll tell you in somewhere in. What do you call it? In less than 6 months. What's that in days? No, you can't. Can you count full days, or should we count a day as an insights achievements? Okay, let's compare. Right, unclick it. There. So of 250 hours, I've done 40 hours. And what did you do? What was the result? Yours was... It was a lot, wasn't it? Where is it? Come back. Where was it? 11 days. 20... And let's... 262. Sorry. I should have just read what you wrote. 262. So you're like above the Empire business. You're on a new... Honestly, I didn't even know these existed. So how much I look at it. No sound, stuff it. Don't know why. Don't know why. I thought I'd got it, but maybe I don't. When I play the little animation with all the little fingers that do a Mexican wave, well, it's meant to cheer, but it doesn't cheer. So, what can I say? Look how I've spelt that. That's great, isn't it? Strings. Like that. Which isn't helping anyone. What? Hold on. Oh my god. I think I'm dyslexic. Oh, hello, Sue Peepy. You've done 30 hours. That's still good. I don't even remember what I did just then. I've forgotten already. Hold on, this is going to fail. So, attack, strength. I'm guessing that's going to be a player attack. These are all going to fail. But technically, we shouldn't have... I mean, they're not going to fail right now. Being that... Except... Okay, yeah, that's fine. Player attack, and then a strength. So, I guess it's going to be player strength. Not like that, thank you. But I will do that anyway. No, I won't. I'll do it like this. Blah, 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 blah. Hold on, I need to... oh, do I... Okay, hold on. No, this isn't going to work. Am I? Hold on. I've got a bad feeling about this already. Yeah, of course I've got a bad feeling about it. What are you doing, Vince? Dope. I'm trying to wrap it. I need to unwrap it. So literally, I just need to do this. Oh, Mum. I don't know. I think today I've got like a... I think every day I've got it. A bad brain. That's what I call it. Look at that. I mean, where's my brain? Up my arse is where my brain is gone. It's not having it. Now it's working. I feel like that should be a different type, but let's not go into that. It reckons that you shouldn't have to change the last one at all, which I find not too believable. We'll soon see. Player attack. Oh yeah. Yeah, actually, that's a good question. Do you stream? Did I know that? I don't think I did. And where do you stream? Plug yourself. Come on. Definitely want some plug in here. Yeah, just... What is it? Armor? Okay. Just make up stuff. There we go, that's fine. Damage, defense, health. Hello? So where's damage? Health? Oh, I'm going to have to look what it's... Well, first and foremost, you shouldn't have to change anything, it reckons. Pfft. Yeah, okay. Well, we can do defense and health, but... hold on. Health? Yeah, okay, we got health. Got health, defense. Oh, wicked. Thanks. Thanks for this. Well, we know that... Okay, so you're planning on doing more soon, but my ongoing project that I haven't touched in a while is a bytecode interpreter in C. Oh, the test for it are written in Haskell though. Well, that's a combination and a half, isn't it? Good on you. I've never touched C. Whoa, hello, put a comma there. Okay, so we've still got a problem which damage and defense doesn't make. So where's calculate used? Calculate player hit is here. You give it a damage and a defense. Where's the damage coming from? Here. Oh, okay, so they have got to be ints, it looks like. Because damage is worked out of calculating damage, which is there. So that returns an int. Well, unless we want to... No, we'll keep... Should we keep it down as int? I think we should. So that's an int. And then, so we get damage, defense, and then the player health. Okay, so we can get the... So we've got player health. Damage and defense are integers. So, what's the problem? What's going on here? There's YouTube playlist. Oh, you got YouTube. Let's have a look. Oh, hello. What I liked about that though is another classical music listener. We like a bit of that. Do 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 do. Oh, it's gone a bit funky now. Okay, you can't hear that. So it's like I'm dancing. Okay, it wasn't just classical music. Ah, cool. So do you just go through it? Because I didn't hear you. Oh, I guess like that, yeah. I guess it's yeah. I don't know. I found it maybe. I guess I don't mind talking, so it wasn't too much of a problem. New health, but I can understand that it might be. Some notes. Oh, you go that way. Yeah, that makes sense. It's not for everyone, is it? That's the thing. What is it? Player health. Not everyone is keen on doing something like that, are they? Okay, there we go. We made it work. I'll go instead of just going, yeah, well done, we did it. It's so right. The issue was these were all ints, which is great. I mean, technically, I could also turn those. Ah, I get you. So it's English isn't my native language, so that's the issue as well. Yeah, that's totally understandable. I mean, you do well. You type fast, and you. I mean, it's. I wouldn't have been able to tell, to be honest. It is my native language, and I still get everything wrong. So don't worry. You heard me read the. I don't know if you were on the other streams when I'm doing the thinking with types. Yeah, I think about 20% of the words. I'm just saying. What was the one I couldn't get the other week? Monoidal. Monoidal. Yeah, a lot of practice writing, but not much talking. Well, maybe that could be your practice. Hey, see, that's the way to do it. I think. Sort of. Sometimes, yeah, it might work. I mean, I'm not trying to pressure you, but you should totally do it because it's a good way to do it. And I'm sure your English isn't that bad. If you're able to write it, don't worry about accents. I mean, I'm English, so my accent's terrible. Yeah, don't make it maybe. Make it a just. Oh God, that's not even funny. Yeah, however that went, that was just terrible all the way around. So what we did, instead of having ints, we created new types for it. So then at least when we're passing in values, a bit funny, is it though? Really? I feel like you're just being kind. Technically, we could have just done these two ints also. What returns here? Oh God. But from just is just a partial function. Oh dear. What have I started? Come on, keep them coming. I think. Open the floodgates for the jokes. See, that's a prime example. See, I'm meant to be English, and I still can't speak. So I think you've got no excuse. You'll definitely be able to do it. Yeah. So we converted everything and allowed these guys to be cool and. This is cool, and now I know exactly. And by doing that, they're wrapped around these new types. So to use them, we need to grab them out. And that's how come we're able, because also we're still able to do these arithmetics because we know that underneath they're an integer or an int, sorry. And that's to deal with those. And here we're just building up a bunch of lets. So let, and that's a value, that's a value, and that's a value. And then we're passing along information. And how that's working, in case you didn't know, is when we're saying we're grabbing a player and a player. So that's player 1, player 2. And then to grab values out of a product, you basically create, you use the name that you've given it, player 2, and then the value you want to grab out of the product, you just put it in front. So player attack would be this one, and grab whatever the player attack is there, which is perfect because if we look at that type, that would be player attack. And if we look at calculate player damage, which is here, the first value is a player attack. But if for some reason I was to, let's demonstrate that being incorrect by doing 100, it'll complain. Look, no instance for num player attack arising from literal. So yeah. That's potentially why. There we go. And the rest does the same. So you build them up. And then if we look, this is what I'm saying. I could potentially make these not int. But I have for now. Yeah, maybe I shouldn't. Because this is the problem here. These two ints are still... Come on, let's do it properly. Let's do it. Damage and defense. New type. Damage equals... Damage. Look at how it's spelled new type. That's good, isn't it? New type. New type. And what's the other one? Defense. And then at least now we have, whoops, the France. The France, that's where I'm from. What am I doing? Okay, shush. There we go. We've got that, and then these two we can have as, what's the return of that one? That's damage. So let's return here. But oh, check this out. So we're going to get a different error in a minute. There we go. So if we look at here, so it should tell us, couldn't match the expected type damage. We've returned int. So we need to do some of this. We need to wrap it back up. So we need to put it back inside of damage. Because we know that our return types is damage. And then if we look at the... Yeah. Okay, so damage. Well, damage expects an input. Whoa, which is not... Whatever I've just done there. Go away. Oh no, that was it. Oh no, look at the documentation. Okay. But, no, that's not really good. Okay, that's not helped us at all. Does that? No. Okay, anyway, you have to pass that in. So if we do it for damage, and then we'll do it for defense also. Defense, and then we'll wrap it back up. So that works. And at that point, why are these not complained? That's what I'd like to know. Because technically this here should be of type damage. Yeah, fine. And that should be of type defense. Yeah, fine. And this is of type damage. And that's of type defense. Okay. But these are in. That's a bit dubious, isn't it? They should have... This should have errored out over here. Well, or at least down here. Let's have a look. I'm just going to refresh because sometimes that does it. There we go. We've got the errors now. There they are. Yeah, that makes sense. Okay, that's better. So if we replace this int with a damage, but we're going to have to do exactly the same and destructure, or do this here. Do some of this. To be honest, you could just... I tend to minimize the words, but I'm not going to do it. We're going to do it so it can be read. And then, should we have... Yeah, let's just return. Hold on. We could... Oh no, so it takes a defense on it. And I guess it returns, if you look at it, it returns another health, doesn't it? It's like the new health. Yeah, so that'd be the new health. And then we wouldn't even have to wrap it. Let's do that. There. There. Go somewhere there. Wherever that went. Oh, I'm up here. Okay. There. So we've wrapped it back up in player health. This is saying that that's already a player health. So if we then go like this. There we go. We've got it. Does that make sense? So instead of having a bunch of ints everywhere, now we're more explicit, aren't we? We're like, definitely, we can't just pass random things the wrong way around. We know that they've each got, and because we have to wrap them, then that's what happens. You can't really get around wrapping something. So if you look at defense, before we were just returning an int, because technically, if we look at that, that's arms of type int and dexterity is of type int. So we could add in them, or sorry, times in them together would create an int. But because we want a defense, we have to wrap it with defense. So we're using this wrapper to give us even more, what would you call it? Well, even more safety. Safety, yeah, I feel safe. So that's the idea behind him. And, I don't know, yeah, I mean, yes, it's definitely like a bit of extra code. But in the long run, you know now that when you're doing calculate player damage, you know exactly what goes where. And if for some reason someone swaps the values round, then the compiler will tell us. Ready? We can't. No, I'm not going to do it. Just because I'll have to change a lot. But yeah, it will tell us. And in all the places that it's that function's used, it will tell you that that's the wrong way around. Bam! thumbs up for that, isn't it? That's exactly what you want. That's why you want a compiler. The compiler needs to go, hey. You know, you've changed this, and actually it affects it here, in all these different files. Please change that order for me. And you'd be like, oh, thanks, compiler, my friend. You're not my friend, buddy. You're not my guy, friend, buddy. You're not. I can't remember what the other one is. Someone will tell me. You're not my... anyway, polymorphic data type. Similar to functions, data types in Haskell can be polymorphic. And we've messed with quite a lot of polymorphism, or not polymorphism, with polymorphic types already. But let's see what it's saying. This means that you can use some type variable as a placeholder, or as placeholders, representing general types. You can either reason about data types in terms of such variables and don't worry about the specific type, or substitute variables with some particular types. Okay, so that might not make too much clue as of yet, but don't worry, we'll move on. Such polymorphism in Haskell is an example of parametric polymorphism. Don't worry about that. I mean, yeah, it helps, but that's not gonna help with your intuition. It's just kind of big words. So the process of defining a polymorphic type is akin to an ordinary data type definition. Oh, I need to read word. You know when you read sentences. So the process of defining a polymorphic type is akin to an ordinary data type definition. It's like there was a dot there and then I said it. The only difference is that all the type variables should go after the type name so that you can reuse them in the constructor fields later. Come on, just give us an example. Damn you. Okay, so what we're talking about, polymorphic, is this A here. So what we're saying is when we've got this data type of foo, it expects a value of A, and that has to be a type. So if we were to use, if we were to declare in a type signature, for example, so my func example, and we want that to be a foo int. Okay, that's going to be a foo int. So we know that A are then going here. This could be absolutely anything. It could be a C, but obviously it'd have to match. We want to put the C back in. Okay, so we're saying at that point right now, A could be absolutely any type that you want. Okay, in its use there. So that's basically that's why it's polymorphic, because we're just saying, well, it's just like a value. I just want like a little placeholder which I'm going to pass stuff on, and then it's actually going to be used here. You'll see it can be used more in depth. Prime example actually would be blah, 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 blah. So it'd be like this. Maybe A. This is one you've probably seen. Just A. I should probably put the nothing first, but it doesn't matter. Nothing. There we go. So maybe you've seen that. So that's the maybe one. So we can see here an A can be anything. So when you think about when we use maybe, yeah, you pass like you'd have like maybe int in. Okay, so we know that it might be an integer or an int, sorry, or it might be a nothing. So in here, it would be just as valid to be. This would work. And then, or otherwise, it could be just, what should it would have to be like 33. There we go. So we're using this int is going to go in here. Okay, and much like this. So this is polymorphic. Cool. So note that both product and sum types can be parameterized. Okay. So actually, we've already seen polymorphic data type. Remember list from chapter 2? Yeah, I thought we'd already seen it. Hey. Like pull that one on us. I'm pretty sure I'd already explained a lot of this, but let's keep going. To give an example of a custom polymorphic type, let's implement a treasure chest data type. Our treasure chest is flexible and it can store some amount of gold. Additionally, there is some space for one more arbitrary treasure, but that could be any treasure and we don't know what it is beforehand. Yeah. So it allows us to create a treasure. So here we've got a treasure chest with an X. So you can have some gold inside that treasure chest, which is an int. But then this specific treasure chest that you're making It also has some loot that can be of any type that you've passed in a type declaration. So whatever you've passed in, they'd expect that to be exactly the same type. So you can see the treasure chest can store any treasure. Indeed, we call it treasure X. X marks a spot. And when writing functions involving a treasure chest type, we don't always need to know what kind of treasure is inside besides gold. Yep, we can either use type variables in our type signature. Here we go, this is where I was demonstrating. So if we want, oh okay, what is this saying? So we can, we can keep going. We can keep making things polymorphic if we want. So how much gold is in my chest? Treasure chest of X and then int, and then it's going to grab the stuff out. So it'd be like, you know, I guess equals. Hold on, and then the value would be. Oh yeah, but anyway, let's not. Actually, I'm not going to go into it just because we'll keep reading. I get carried away sometimes. Or we can specify a concrete type. So we can leave it still polymorphic or flexible, or we can give it a concrete type. So now we're going, I want it to be a diamond of the, you know, whatever it is, I want it to be of type diamond. That's what our X is going to be inside of our treasure chest. So this is going to be a diamond. But if we're saying X here, because technically it's saying X because it looks like, look, how much gold. It's only going to grab the gold out of it. So it doesn't necessarily care what that value is going to be. It just wants the gold. So that's probably why it's being used there. Another one. Is enough diamonds? Treasure chest diamonds. Yeah, that's what we saw. In the same spirit, we can implement a function that creates treasure with some predefined amount of gold and a given treasure. Yeah, here we go. So make chest. Make me a chest. So it takes an X. Again, that's going to refer, because we know that when we make it up here, that can be anything. Again, these are just whatever you want to call them. So it says X here, but it could be Z, whatever. And then it returns us a treasure chest using that same type that you've passed into it. So this is leaving it flexible. We're able to create a treasure chest, but we're still leaving it flexible as to what that value is going to be. But in this one here, so the X is going to be treasure. And we're going to have a treasure chest, which is what we're creating here. And we want to make the treasure chest gold be 50. So that's like predetermined. And then the loot is whatever we pass in, which is our X, which is the same X that's included in our type. Okay. So that's what polymorphism is. It's basically literally just saying this could be anything. Hey, I forget if it's Leo or Leon you prefer. I think it's Leo, so I'm going to say Leo. Look at that thing. What's that emoji? Oh, it says hi. Kind of, maybe I need to maybe that's the next thing I can do. I can like make my own emoji. I didn't think about that. That'd be quite fun, wouldn't it? Make like a little emoji. Do you need to do some like, what do you call it, the art when you pixel? Is it pixel art? I've never tried that. I could find one, because the way I do all my art is I find someone that's really good at it, get it, and then copy it, and then just turn it into my own. Because, you know, I'm not actually a good artist at all. So, polymorphic algebraic data types. Eat that for your dinner and munch on that. Okay, so we know polymorphic, and we do actually know algebraic data types. So it's an algebraic data type that's polymorphic. Are a great deal. One of the most common and useful standard polymorphic types is maybe. There we go. Where did I make it? Where's maybe? There's maybe. That's the most famous one. So that's an algebraic data type. It represents a notion of optional value. Maybe the value is there, or maybe it's not. Just watched a recording of yesterday's stream. Couldn't watch it. Like, oh, yeah. Yeah, I went... Oh, that was really annoying. Last night, I edited that video to cut out all the cruft. Because, you know, I go off on tangents, like I am right now. I went off on a tangent for about 10 minutes, and I was like, well, if you want to learn this stuff, you probably don't want to listen to me gas about some crap. So I've edited it all out, and I was like, cool, cool, cool. And then I used, what do I use? I use Final Cut Pro, and it's got an option where you can export to YouTube. It's like, cool, I'll do that. Just exported the original file. None of my edits. Couldn't believe it. And it takes friggin' ages. So I'm not doing it again. So yeah. Yeah, thanks for watching it though. And then after I did that, I started reading the book again to think, okay, I'm gonna go a bit ahead, you know, just to make sure I have a slight idea of what I'm doing. Did I fuck? No. I got to like chapter 6 and I was like, oh, my brain sucks. And then to get around that, which is probably what everyone should do already, is I watched. Yeah, so I started watching because Chiroptical. Yeah, thinking with types. When am I going to do it? Maybe tomorrow. Is it Friday? What do I do on Fridays? Nothing. I'm getting quite consistent with starting at 4 PM UK time though. Or is that PST? I don't know what it is. UK time. I'm getting quite good at that, it seems. I think the next step is, yeah, making that more regular. And it's whenever I'm bored. So I've narrowed it down to 4 PM ish. That's not bad. I've not narrowed it down to which days though. Sorry, I can't perform that well. So yeah. Anyway, I started watching that. Let's have a look. I'll link the playlist. There's a playlist if people want it, because someone's already done it. It wouldn't be too bad for you. Cool. Well, if you're willing to come, let's do it. So yeah, this is a place that already exists. Because he was on the stream last night. Wow. But yeah, I was looking. He went pretty damn in depth. So he actually started doing the endomorphisms and stuff. You know, we were just here. We had to try and find which one of these was a functor. Sorry, beginners. Sorry, I'm just going off on a rant. Sorry, because this is definitely not beginner friendly. I'm going to go back. But yeah, so he went really in depth, and he's got all these nice little comments. Professional. Unlike myself, so yeah, I think the next stream is a stream that I'm going to be. I'll need help. So we're going to have to try and get some. You know, I think you know your stuff. Or we can just struggle together, and it'll be fine. So Haskell doesn't have the concept of null. Thank goodness, because null is your enemy. Because at least here, this is what's really cool. Hold on, is it going to tell us? If you want to work with potentiality absent values, potentially absent, I'm just making up words, use the maybe type explicitly. So, what was I going to say? Sorry, I just read your message to PP. But yeah, hi Leo. Alright, Sue PP. It is Sue PP, yeah. I'm waiting for you to do a video, or do another video, Sue PP. And I expect some sort of speaking. Or maybe you could do, you know, if you type your comments, you could add it to like one of those robot speakers. You could somehow. Okay, that's going to go bad. Yes, no nulls. Why is that good? Because we can be. This is way more informative than it. You know, we're getting an actual type back. We're getting a value. So if something's not there, or whenever we use maybe, we're saying we can use it or we can't in loads of different. I think the scenario we saw it in is when, you know, we can do a nothing of something, a just of, well, they have to be the same. So 2. Oops. 43. Okay. So how that's really useful is we're saying, well, the very first is literally nothing. But if we're passing around nulls, and we have to try and do null checks, and you get all sorts of hellholes from doing that. But here we can literally, when we end up using it in the function, we can do a case match of whatever we've called that value we've brought in. Blah 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 blah. Yeah. So yeah, and then of that's. Imagining that we've mapped over it and we're just looking at every single one at a time, and then we can just say, oh, if it's a nothing, then do that. If it's a just, a just of A, then do that, and then do whatever you want to do with your A. Okay, so we've got that power. We can be really like down to know exactly what these are and what we're going to do with them. But when dealing with null, you know when you do null checks in like JavaScript. Uh-oh. But this is like, we've got the compiler that's going to tell us, yeah. That, because you know you've got multiple values, multiple meanings for null. And is there a good way to avoid null pointer bugs? Maybe. Oh, that should have been. Look, I'm all down with the dad jokes, but hell, is there a good way to avoid null pointer bugs? Maybe. Isn't that good? Hold on. No, where's my thing? Hold on. Ah, no, I'm missing a trick here. Here we go. It's coming. Yeah, sorry about that. Totally wrong thing. Press the wrong thing. Go back to this. Go away, you. I was just talking and I realised my mic's turned off as well. Am I back to normal now? Yeah, I think I am. Technology. Software engineers, whoever made that. Right, back to it. Another one. Another standard polymorphic data type is either. It stores either the value of one type or the value of another. So either can be used in multiple scenarios, but the one that's usually the way I think of either. So either is a type that expects two values. Okay, so you see that's obviously left and that's right, or 1 and 2. So the left is an A and the right is a B. And the way I think about either is, well, I go with right first. Right is right, you know, because it's right, and left is bad, because right is right. So it's usually like, it's very much like just, except what you're doing is you're able to pass along a value. With nothing, you're just saying it's nothing. It's like, phew. I'm just I'm letting you know that it's nothing, but that's all I can do. But here, you can actually say, well, I want it to be a type. It can be left of a type. So, and it will do all the pattern matching will be the same, and it will work in a similar way once you get further into Haskell, where the left will clearly, you'll see that left is clearly like the bad root, good root, right root, bad root. Okay, so it can help to explore types of constructors, nothing just left and right. Let's stretch our fingers. Oh, I need to get that. That's a perfect time for the... I can't do it. I'd have to... Someone, quick. someone follow me so then we can get the fingers going. Otherwise, tough tits. I didn't do it. Sorry. I'd have to go on something. And then I'd figure out what I was doing. Okay. Just level it up. Let's stretch our fingers and blow off some dust from our GHCI and check that. Let's check it. You can pattern match on values of the either type as well as on any other custom data type. Okay. Excuse me. So show either is either a string or an int, and it returns you a string. So if you pass show either a left with a string, then it will say left with string plus that string that it grabs out of left. So it's grabbing that piece out like that. And then it show if you pass it a right with an integer, it will return you right with number. And you have to do show on that one because obviously we're doing a string here, and string plus plus an integer equals error. So you have to do show, which will convert the int into a string. Okay. Is that us stretching our fingers, you think? I don't know. Let's have a look. Well, I've not stretched my fingers at all, but I've talked through it, so I've stretched my vocal cords. Now, after we covered polymorphic types, you are finally ready to learn how lists are actually defined in a Haskell world. Behold, the might list type. The mighty, I'm going to put it in. The mighty list type. What is going on? So data, let's have a look. Immediately we know what all of that means. Okay, well, do you? Well, in case you don't, data that A is equal that, or It's an A cons into A inside, or a list of A's. So data list of A is equal, that's like our empty list. Makes sense. And then this is our list with values. A cons onto a list of A's. So let's have a look. The colon is simply the constructor name for the list. Oh, okay. Yes. Oh, I get you. Constructors in Haskell can be defined as infix operators as well, written after the first argument. Oh, sorry, i.e. be written after the first argument. So this, technically, if we wanted, can be seen like that. That's how it works. But here, it's infix. That's the other way. Is prefix because it's before, infix because it's in there. Okay, let's keep reading. I'm not sure how to explain. So kind of like immediately we know what that means. I mean, should that be like that? Because I don't know. I mean, it might be. Whoops. I'd go like that. So I don't know if you started off in Haskell, you'd potentially know what that means. So let's keep going. I think it's a joke. So they're going to explain. So written after the first argument. So, constructors in Haskell can be defined as infix operators as well, i.e. be written after the first argument. The same way we write 1 + 2 and not that. Because if it was like that, that'd have to be like this. Oops. That's prefix and that is infix. But only if they start with a colon. The colon, but only if they start with a colon. The colon is taken by lists. Now you see why we were able to pattern match on it. Pattern match on. Whoa, I don't know what. I'm not really sure what this means. The type name uses built-in syntax to reserve the square brackets. Okay, so this is literally just a name of it. It's not actually empty list, it's just like naming it. So if we wanted, we could have gone with, no, actually let's go with something funky. That's not funky. Yeah, there we go. We could have made, but I'm unsure about this. If I don't think that's gonna swim for some reason. I think that's wrong, but let's keep going. Let's put it back. Actually, don't look at that. It's gonna make you ill. Definitely don't look at that. There we go. We're back. We're back. Square. Now you see why square brackets exclusively for list, but otherwise is a simple polymorphic recursive sum type. I'd like to get them in. Get this in is a simple polymorphic recursive sum type. So in here, we're able to create recursion. How list is? I don't know. Shall we look? I don't think so. Apparently. We're going to try and answer this question for you. You got to find a result. No. Let's go in list then. Or is it a special syntax to make things like foo work? I'll be honest, I don't know. I've always wondered. I've never sort of come across and gone, actually, let's find out. I guess if we go to this source, it's going to point us somewhere where there. Oh no. Default. Oh, data ball, ordering, string. No. Sometimes you can kind of like click. I can't see one though. Especially when you type in the wrong thing. So there's one. There's that. So that's no good. I don't think it is good. Oh no. Oh, go back. Is that gonna... I don't know. I'm actually confused. Because it seems... I don't think it would be here though. Oh, hold on then. Why can't we click it? I don't know. I don't think... Because look, because if it's something... Look, we can click monad, we can click applicative, but we can't click that. So I don't know if it's just... But I can't see where it's declared. Which... No, that's for plus plus. You'd think it'd be nearer the top. Oh, hello. It's in base. Haskell always has the answer. Cool. No line numbers. I love it when it does that. Tail. Here. Where am I looking? There's head. So it's got to be in here somewhere, isn't it? Is it just going to be like the same deal? It's up here. What? No. So it gets head. So where's it getting it? Not Haskell 98. Okay. Should we go back to 100? No, it's not going 100. Let's keep looking for it. It'll be in here somewhere. Last. Length. Filter. Unless I'm missing something, let us know, Haskell. Beep. Cycle. Drop while. Take. You'd think it'd have like some sort of... I don't see it. What's this? No. It's GHC. Why? Because it literally just declares head, doesn't it? And it's kind of like just... But this is commented out. So not Haskell 98 built-in syntax. So it must just be built into the compiler. That's my potential thinking. I don't see where this is declared. Ah, there we... Vlad's coming into the rescue. It says built-in syntax in the export list, so I guess it is. It's special. Ah, okay. Hence we can't find it. That makes total sense, doesn't it? Yeah. I was kind of right about something. That's cool. So yeah, whatever. We don't need to learn that. It's all built in. That's the way. That's the way to learn. Yeah, stuff it. It's built in. Don't worry about it. Okay. Now you can see why we were able to pattern match on it. Okay. Okay, I can see. The type name uses built-in syntax. Oh, so yeah, basically, Vince, yet again, read and read and read where you're going. I find that sometimes that I keep doing it, but I keep getting to a point I'm like, okay, well, let's try and work it out. Okay. And then I go off, I go down the rabbit hole, try and find it, and then literally the next sentence is there. Oh, one day I'll ban you for distracting you with my questions and comments. Nah, never. I like it. It makes it interactive, doesn't it? That's exactly why I did this. So questions could be asked, because this is what's key with people. That's why I don't ever want people to think questions are too dumb or anything, because I didn't know. So literally from your question, which you might have thought was a bit of a distraction, whatever, was actually cool because I didn't know that, and now I know. So it's a benefit to me. And that's the same with anyone, even like, that's why I hate the belief sometimes that, say, like juniors and things are just a burden, but they're not. They're going to ask you things that you might not have thought of, or especially show you things that you might not have thought of, and that's great. That's what I want. Yeah, more questions, please. Not personal one, or you can if you want. Try it. I'll leave it to piss off or not. We'll see. I had to go off on a tangent, didn't I? I couldn't just keep it. Okay, so here we go. Keep reading. to reserve the square brackets exclusively for lists, but otherwise it's a simple polymorphic recursive sum type. Just, you know, just a simple polymorphic recursive sum type. Otherwise, if you rename some constructor and type names, the list type could look quite simple. Or could it? As any of us could have written it. Any of us mere mortals could have written it. Data list, yeah, so this is generally how you see it, don't you? That is exactly this, essentially. Look at it. It's exactly the same. And this makes more sense than that for whatever reason in my brain. So I know I've got a data type called list. I know they've even yeah, I know. Where was it? It's a built-in syntax. Does it say special a bit further down? Somewhere. Yeah. Should have read on. No. Don't want to go forwards. Okay, so we know that it's either an empty or it's a cons, you know, like when we do a just or a maybe. A and then a list of A. So then it goes back in that way. So that's a recursion. It's like it's either a cons is an A, so a cons type takes an A and another list of A. So that's how you end up building up. Well, that's how you cons an A into this. Yeah. Okay. So we use to group. What? How about brackets? Brackets? Yeah. To group list with an A type variable in the second field of the cons constructor. This is done to tell the compiler that list and A should go together as one type in harmony. As one type in harmony. In harmony. So before entering the real world of adventures and glorious victories, that's what I'm all about. Not just adventures, but also glorious victories. I'm not mocking how it's written. I just like to interpret how it's written into my own way. So we should prepare for different things in this world. Damn right. This is what we're doing. It is always a good idea to understand the whole context before going for a quest. It's always where was it? It's always good to read on before going through the rabbit hole of a quest. And before fighting a dragon, it makes sense to prepare for different unexpected things. So let's define data type describing a dragon layer. Oh, I don't know if I want to describe a dragon layer. Here we go. So a layer has a dragon and possibly a treasure chest. So let's go. Have we got a layer? Yeah. I'm going to make it like this. Are we... Hold on. Let's first and foremost... No, I'm going to do it like this. I've decided. What am I doing? So it has... Where was it? A dragon. Okay. So it has a dragon, which is going to be of type dragon, which we don't have yet, and possibly a treasure chest. Let's just call it a chest because I don't want to type out treasure chest every time. Okay. Oh no, it's a maybe because it might have it. Okay, so it's a maybe treasure chest as described in the previous section. A layer also may not contain any treasures, but we'll never know until we explore the cave. Okay, so should we say it's a list because it says any treasures, or is the chest is like treasures, isn't it? Okay, let's just create some data chest. What should we say? It could be anything. Should we do some of this? Or should we just make it a new type? Let's do it. A chest A is... Oh no, that's not going to work, is it? No, it is. Sorry, that's not actually a pipe. It's just my things come up. And what's a dragon? A dragon can have a unique magical power, but it can be literally anything. And we don't know in advance what power it has. Oh, you got to go. Cool. Thanks for coming. I'll see you soon, SuPP. Another dragon can have any unique magical power, but it can be literally anything, and we don't know in advance what power it has. We literally don't know. So I mean, dragon's going to look very similar to chest, and I think chest is wrong, but that's what it's saying, isn't it? A dragon. Oh, hold on. Should we say a dragon? Should we give it? Actually, let's make it a little bit different. We'll give it a power. Is that what they called it? Can have a magical power. Magic. There we go. That's the same deal. Except dragon's not going to be happy. Expecting one more argument. Yeah, okay, that's fine. Ooh, yeah, that's throwness, isn't it? What should we say? Can't just give it anything. Because we want it to be any type. But we can't just make it any type here. Oh, okay, this is coarse. Unique, but literally anything. We don't know in advance what power it has. Because the only way we could pass it is if we pass it here. Hey, Aventinus, thanks for following. If I had sound, you would have heard people shouting and screaming like a crowd. But you got the animation, so, you know, it's a win-win. Or win-lose. Lose-win. Win. And see, I mean, I'm definitely going the wrong way with this, but let's just do it. Why not? Except I can't work it like that. I'd have to work it like this. What beast have I created? But we can explain what's going on, can't we? So we can say a layer, and we can tell the A would be the dragon. So we want to say what magic power does a dragon have? This is... I know I keep saying it's wrong, but it's definitely wrong. Hint, maybe that some standard types we mentioned above are useful. Okay, hold on. Create a data type that describes such dragon layer. Use polymorphism to parameterize data types in places where values can be of any general type. Well, that's the only way to, you know, if we want these to be any type, we'd have to pass them along, and then we'd have to get them, you know, at some point we'd have to tell them what types they might be. And this is the place up here. It'd be my educated guess. So I can explain that. Let's split them apart a little bit. Yeah, so we've got a layer. So if we were to use layer, we could go, you know, if we were to use it inside type. Oh, there we go. My funky funk. Okay. And that would be of type layer. Let's say the dragon have magic of int. And the chest would have the content of string. So special there. So it's called mufunk. My funky funk. Yep. And that would equal whatever. Doesn't matter. Okay. So you'll see that type check because we're setting up a layer and we know that int, so that'd be the A, and that's actually passed into dragon. Oh, actually, hold on. Oh, but what? No, hold on. What if we were to do A, B? It's going to be happy. Wait, that's not too bad. So we can literally define it inside of here. So that would be a... yeah. So that'd be a layer. Cool. And then from here, we know we want to return a layer AB. Yeah, so at this point, we could... whoa, hello. Oh, my computer's starting to... Check this out. I will open Activity Monitor. Let's open it up. Let's have a look at the one with the most CPU, please. Wirecast is what I use. 125 CPU. Oh, wicked. If I look on the actual CUI of it, it says... Let's have a look. It says 12%. Why class? You're lying to me. And why are you using so much CPU? YESOD. YESOD is like the framework YESOD. I think its interpretation should be YESOD. Right. A layer of... Well, we need an A and a B. But actually we could just... yeah. I don't know where I was going with this. I just don't remember. I can't remember what I was going to do. Yep, totally forgotten. There we go. What was I trying to say? I was trying to determine that these two... That's what I was trying to determine, wasn't it? But technically, yeah, they'd have to be whatever you pass in. So yeah, so let's say... this is what I was trying to do. So we're keeping things polymorphic here. And then we can return... at this point... We can return that, yeah. I don't know what I'm doing. Actually, let's have a look at something. What does it expect? It's a found hole of maybe chest B. So we could return it like I've done here, or we could actually use an object and then fill in the values, and then we could fill in our A and our B to be whatever we wanted from here. But then we'd be ignoring that A and B. Or we could just do it like this. Polymorphic. No, polymorphic. So your question, isn't it so polymorphic that there's just one possible implementation left, which would be ID? No. Polymorphic in this instance means that these A's and B's can be whatever we give it. But yes, once you set it, then we've made the type concrete. But in that example I was just showing, so at this point, see, look, make my funky funk is still, so if you look in the type, we're still saying it's polymorphic. Let's delete that, okay? And then here we can literally, look, we can do this. So we can go dragon equals, and it would be dragon, I don't know, let's give it that, okay? Ah, did you misread it? Yeah, sorry. Well, I'm not sorry. You should be sorry. You misread it. I'm just kidding. And then this, let's say, oh no, let's just make this nothing. It's going to want no incident arising from literal 23. Okay, so let's... Is it going to want something like this? No, it's not. Yeah, okay, so... We've not told it it'd have to have that. It'd have to have that. But we created our own layer, and we've left. Actually, it must have converted it to. That must think that B is of maybe. No, because it still doesn't know, because I've used nothing. So if you look when we use maybe's a maybe A, just A nothing. Okay, so because we've made it nothing. We're leaving that B being polymorphic. So chest, at this point, my funky funk layer. We've made the dragon concrete by giving it an int. But we've got around the chest by making it a nothing. So it's still a maybe of whatever, but it's a nothing. So we've kind of cheated there a little bit. But if we were to go... So let's change it. If I was to say just, I'll get an error. Yeah, because it's expecting a B. See, we're saying, well, actually, chest, what you've passed me along to my type is B. I don't know what B's polymorphic at the moment, so it'd have to be string for it to work. Or is it still defining base string? What's the matter with you? Oh, what? It wants that. Okay, well, just for now. Because, okay, so it's not going to be happy. Why aren't you happy? See, type holes. Type holes will give us a... Let's have a look what I've done. Oh, of course, I'm wrong. Here we go. That's why. Derp. Hello gold. There we go. That's fine now. So does that make sense? I think that makes sense. So we've declared our own layer. We're saying inside of it's going to have a dragon. He's 23 magic, like Jordan. Jordan was number 23, wasn't he? There's a chest in there actually, and it's actually got a value. And that chest has got the, well, where was it? The chest has just got a value of string. And that's how we do it. So you can see, so here's that, and then we can literally, if we wanted, this is where it comes. We could swap these around. Okay, it's going to fail. Hold on. Well, first and foremost, it's going to fail because I've done that. And then here's going to fail because we need to swap these round. Whoops. Yo. Cool. So that's how come things are polymorphic. We can make the A and the B whatever we want. So we see we've got this layer, and that refers to the layer having an int and a string. So our dragon's an int, and then the content of our chest is a string. But then in this one, we've made a new one, and it's the other way around. And so actually, our dragon, if I do some spacing, is a string, and then our chest is an int. Yeah, so that's what polymorphism is. Cool. Where are we now? Type classes. What is the time? 17:55. Okay, I've still got a little bit. Yeah, that wasn't too bad, was it? I think that made sense. Type class is a regularly used way to express common characteristics of the different data types. In some sense, a type class describes the interface of some value without. Oh, I've been sat on my ankle. Oh, it's gone stiff. What have I to do? I've done that for. But I'm not. Have I? No, my ankle's like been under my knee somehow. I never sit like that, and that's probably why. I've lost where I was. Regularly used in a way to express common characteristics of the different data types. So now we're kind of going up a level. In some sense, a type class describes the interface of some value without telling you the implementation detail. Okay, we'll keep going. Instance is a representation of the type class. Have we created instances yet? I don't think we have we? Ah, this is cool. Is a representation of the type class. So you end up creating a type class. So you okay, we'll keep reading because otherwise I've got a feeling I'll go off and then I don't want to. So representation of type class to data. Oh, I need to I needed to burp and yawn at the same time. That was awkward. Is a representation of type class to data type relationship. In order to show that the data type obeys the type class rules and use the methods of the type class on a data value, you need to provide the work instructions under this particular type class, and that is the instance of the data type for the specific type classes. I mean, that could have been explained nicer in code, but let's keep going. I hope there's an example. Here's an example. Okay, I think we should let's move this up because I think this should be further up because it's kind of like explaining, and then as you're explaining it, because you got all this wall of, I mean, perfectly fine, it's correct, but I find it easier to sort of read this stuff and then point to what it means. Okay, so we've got, this is a type class. I like this though, that's nice, isn't it? So we've got a class of arch enemy of A, okay? And on it we've got a method. So this it tells, oh, that's popped out by one. There we go. So this is a type class name, yep. That's a parameter. So for us, we're just giving it an A. And that's just a where keyword where, we've seen it before. So get arch enemy, that's the method on it. And arch enemy takes that A and returns us a string. Okay, so that's essentially a functionality that exists in the ether. of archenemy, and that's how it acts as a class, a type class. Okay, and then an instance would be instance. Does it show lower down? Let's see the one they've used. Here we go. Let's see. I think they've done an instance of bool. Yes. So in this scenario, what am I doing? E 1 2. There we go. So in this scenario, we're saying, okay, well we want to tell the compiler how it should behave if that A is bool. Okay, does that make sense? So we want to tell it how should it behave, and then when we do that, we have to use this method name. So the method that we have on archenemy is getEnemy. That's it. So here we're saying, okay, well, if you use archenemy with a bool, this is compiler goes, hey compiler, this is how I want it to work. And if you look, essentially archenemy is just like show. It takes that A, so it'll take that bool, and it wants to return us a string. So if we look archenemy, so that literally, look, that gives us our type. We know that it takes an A, so for our case it's a bool, and it returns us a string. So we pass it an A, which is true. And we know that bool has two values, true and false. And it just reacts. So we've basically created this new class of archenemy, which is suspiciously like show. And you can give it an A. That's a type parameter, which for us is going to be a bool. And then we're going to say, compiler, anytime we use archenemy anywhere with a bool, this is how I want you to behave and work. And it's like, okay, well, if you pass archenemy true, then I'm going to return you false. Or sorry, if you use get archenemy, because this is a method within it. So if we look at things like, let's have a look at another one quickly. Hello. We were looking at this. Let's look at functor is another one. There's a class functor. We won't delve too deep into it. Let's zoom in a little bit. Oh, and just totally lose where we were. That's cool. Where were you? Functor. Data maybe. No, let's go down. Oh, we've lost you. No, actually, if I click on it, that'll take us to it. There we go. What? Hold on, here we go. Oh, right, okay. Hey, Ezo Blaze, what can you make using Haskell, though? Nothing. It's all pure. We just like, it just ends up going around in just purity. A world of the purest of pure. It's like the diamond. Lots of stuff. Prominently back-end applications. So you'd be looking at loads. I don't know, APIs, streaming, loads of stuff. Essentially, yeah, you can make a lot of stuff. I mean, the last thing I did, it wasn't Haskell, it's PureScript, but similar. We were working on a distributed system over a VPN that instead of handling images, it did video streaming. So yeah, it can do pretty complex stuff at, is it Facebook? Yeah, Facebook. They use it for the spam filter. So, you know, millions and billions of things go through. So it stops when people write things. It's like the first port of call to try and stop spam. And then, you know, it will go through other processes. So yeah, so it's using big companies. And it's just picking up popularity, basically. And that's why I'm just doing these basic instructions. But other than that, it's just a bunch of what do people say? It's like you know, people sort of sitting on top of their thrones of intelligence. The problem is essentially it comes from an academia background, a really strong one, and it's used to also make languages. Like a lot of languages can be made using Haskell. And because of that, and because of the academic background, how, you know, it's also used for type, like, well, yeah, just Haskell can be used for lots of things at a higher level that are more academic than production wise, and it's been used like that primarily for years. But as it's becoming more and more popular, things are starting to change now within the community to make it, one, more approachable to newcomers, and two, you know, the actual language itself is changing because of the way, you know, the production Haskell's becoming more widely adopted. So yeah, it's no Java in terms of like popularity, but the thing is you'll find that most people get onto Haskell, they're like, oh yeah, this is interesting, cool, let's find out, you know, let's see what it's like, and then they go, oh, actually this is really good. The language I've got is like hasn't got all these really nice features, and the primary one is the compiler. And I don't know, if you watch on for a bit, you'll see I do all sorts of stuff with the compiler to help me write my code. I've literally got a little buddy by my side, and I just go, hey compiler, what should this be, what should that be, and it just goes, try this, try that. So yeah, that's like its uses, but otherwise, yeah, it's just pure and does nothing. So we're looking at right now, we're looking at a data type of functor, sorry, a class, functor. So if we look, so it was very much, this is another implementation, and if we know that functor has, let's ignore that bit, but it has this, an fmap. Where was I? Oh my god, it's gone on this side. Why are you going on that side for? Sorry, I've normally, what was it called? A method. There we go. Go back to there. So functor has a method of fmap, which, you know, we've used fmap before for mapping over things. If we remember, it's whatever. So for us, we've seen it with the f is a list, and that's a list. So it's a list of A, and we've got a function that converts that A into a B, and then returns us a list of B's. So we start off with a list of A's, and at each element we're going to convert it to a B, and we'll return that list with the new conversion. So when we see it like this, it's like, okay, well that's the class. And then if we look back at the instances, which is what we're building, so for functor we've got a maybe, and then it'll tell us fmap functor, there it is, instance functor maybe, where's maybe, maybe monoid functor let's look for maybe then, maybe should we do functor maybe, is that going to find anything? Yeah, it is, there we go, exactly the same as what we're doing. We're saying, oh okay, so here's fmap, here's our method, we don't care about the f which we expect. So when we looked at it, it was, yep, the fmap expects a function from A to B, and then if the second value of that, and the second value was a list of A, so if that list of A is a nothing, when we use it with maybe, sorry, it wouldn't be with a list, the maybe is a functor itself, sorry, the f would be maybe. Okay, so it's fmap, and we don't care about the A to B, you can see that, and here, the maybe A be nothing. So if we give fmap a nothing, it will return us a nothing. But if we give an fmap a just of A, then look, it returns us another just. Yeah, so it rewraps the just, and then it does that function on the inside of whatever the just is of maybe. So it uses that function A to B, and we pass it A. So this would then be a B. So we return just B. So if we imagine before, it takes a just A, so an fmap, we expect it to do something of, it expects a function A to B, a value of a functor A, so in our case it's just, and it returns us the B, so A to B. Okay, so I think that makes sense. I don't know if I'm going too deep. Yeah, so that's that, and that's how we've written our instance. So in this, before it was maybe, but here it's bool. So say we were to do maybe, and if we look, that would be maybe A. Yeah. Oh, yeah. Yeah, that's fine. And we'd have, I mean, you wouldn't, nothing. And then we'd, let's say, well, actually, it couldn't do much because our return type's a string. It's always going to be And then if it's a just, hold on, I've got to wrap it. Whoops. Stop. I think once I stream past a certain amount of time, things slow down. And then here, because we want to do a string, we could take the inner value and do that, show A, and that return us a string. Hoping that our A has a show instance, but whatever. So yeah, so we're able to, you know, tell the compiler exactly how we want this specific class, or this the method as part of that class to interact with other classes, like a maybe, yeah, or data type, sorry. Cool, so let's consolidate the type class as instance concept, the analog from fantasy world. Okay. And many lovely princesses need to be rescued, and those, oh, I don't know if we're going to read that. Next, let's look at one code example for a better illustration of the instance type class relationship. We can define a type class that would tell us one's arch enemy. The type class, the syntax is as follows. You need to use a class keyword. Yes, we've done all of this. I've explained all of that. Okay, and then we've got this method getEnemy. Yeah, that makes sense. And then when we start, oh, here we go. Look, they've totally converted it. So we've got, there's for bool, an int. Okay, so it's int to string. So arch enemy pass an int. And it checks here, this is literally just made up. You know, it could be whatever you want. So case I, if that int is a 0, then return division, the string division. And if whatever else, if it's anything else, return derivative, the string. And with double, similar vibes, except they've just done a guard here, which we go on, I think it's in lesson 2, guards, but it's just basically saying, instead of doing a case, we're just doing it in line here. So we're just going n is none n, is infinity n, otherwise, so yeah. So if it's, these are functions, so it literally just goes, it'll hit these one by one. So it'll go, okay, is it a none? No, don't do anything. Is it infinite of n? Then no, because these return true. So yeah, sorry, in guards, this is a true or false function. So we're doing a function. If this returns true, do that. Otherwise, move on. You know, and then otherwise, which is the very last one, whatever else happens, I want you to return. You know, if none of these two match, then return none. So you see, we've created this. We've just got this weird type class that, you know, arch enemy, and then we're just using things that already exist and saying, well, I want you to behave in this way when you pass me a double. Yeah, and I want, this is the method that I've got under here. So it's like fmap I showed. You know, we end up making all different types of functionality of fmap, but then what that means is you can use fmap over loads of different functions, sorry, over loads of different data types, like maybe like list, like whatever they all the instances that are available for it, which when we look, they're all kind of, well, they're dotted around this file, but there's loads, whatever's with functor. So if we were to look like functor, instance functor, non-empty, so we've got, there's the non-empty, you know, there's the one for list. Let's go up. There's list, and the fmap for list is literally map. Yeah, so that's how it works under the hood. So sometimes if it's saying you get an error message saying no instance num blah blah blah, it literally, it means that you're trying to use something that's, say, I don't know, whatever, a maybe, for example, and then you're trying to use it against a functor, but for some reason that one doesn't exist. That's usually what that means. It just means that there hasn't, you either need to make an instance, or there's a bloody good reason why there isn't one. And the usual one is when you're trying to mix up your strings and ints. It'd be a good one, because it'll say no num of string, something like that. No num class of string, no instance num of string, something like that. I can't remember the exact, but yeah, that's usually your error. So, and then you can write a polymorphic function and not worry about which specific type is understood until, yeah. So this is where you get that freedom. So now we know that fmap can be used against anything that's of the class functor. Okay, so if you're using a function and for some reason it doesn't have a functor class, then you can't use fmap with that specific type class or data type, sorry. So okay, so for that we are using constraints in Haskell. It is the identification of affiliation to the type class. Okay. The constraints should go after the double colon sign in the function type declaration. You can specify one or many constraints. If more than one, they should be in parentheses and comma separated. The end of the constraint is determined with the fat arrow. Oh, okay. This is explaining something. This is explaining constraints. Okay, so this is a function, and a constraint is basically saying that the A is of, we're sort of parameterizing, or we're saying that we're going to give a constraint, and it should be of the type class show and a type class arch enemy. Okay, so for it to work in this function, we need to make sure that A has an arch enemy representation. So we can use there get arch enemy in here, but we can also use show. Okay, so we need to make sure that those two are definitely part of the A. So then when we use, this A is now converted to X, and then the whole function returns a string. So here we see the actual function is just here, and this is the constraint. So it's kind of like a medium polymorphic. So polymorphic is when it can just be absolutely anything you want. So if we were just to do A to string, it can be anything you want. Go for gold. But here it's going to be constraint to arch enemy and show. Okay, and we can see exactly where it's being used. So we can see that we know because A has a show instance, then we can use show. So X, we can use show of X. And then here, get arch enemy. So we can use that because there's an arch enemy. And if we realize show and arch enemy are exactly the same thing, essentially. So yeah, get arch enemy X. And when we look at get arch enemy, we see, it always returns a string. So yeah, the behavior of this polymorphic function depends on the data type used with this function. Such dependency is called ad hoc polymorphism. Okay, this is how it works in action. So there it is, reveal. So we do reveal arch enemy 42, we pass it, okay, and we say it's an int. So then that becomes an int, and that becomes an int. Okay, so then we pass the int to there, so it looks at that instance and goes, oh, okay, well my A is an int actually. What do I do with ints? Okay, I'll look here. Okay, this is what I do with ints. Oh, okay, so I just if it's a 0, then I return division. Otherwise, I'm going to return derivative. So then here, if you were to use it, because it's been made to int, there we go. Can you see it's returned derivative right there? And here it's returned the string 42. But if you were for some reason to make it a double, so if it's used and you were to type and you were to say double, then it'd go through these functions and it'd be either infinite, limit, or nan over here, which is pretty cool, isn't it? You're kind of got this weird flexibility, but you're you can reuse things, but you're also being very deterministic, or you're given a very good example how that works. So yeah. However, if we try to use this function with something that doesn't implement an instance of our type class, we will get a corresponding compiler. Here's a compiler that would warn us precisely about that. Cool. So reveal arch enemy, an adorable string that has no enemies. But obviously you're not, let's have a look. We haven't got one. So we haven't got one as string. We've got bool, int, and double, but no string, no instance of string. So that'll fail. So it says no instance for arch enemy string. So that's the sort of error you might see quite a lot. So it will mean that the type, because we're using in here, so because reveal arch enemy has a constraint, so we're saying that A has to be of arch enemy. And then when the compiler comes in and goes, okay, I'm going to use reveal arch enemy, I'm going to pass it a string. And the compiler goes, let's go through all my instances. And it goes, oh shit, I've got bool, int, double. I don't have any for string. Sorry, I don't know what to do. If I whatever we do inside, I can't do anything with it. And it'll go, no instances for arch enemy string arise from using it. Yeah, and then the stuff is just telling you where it's happening. So interestingly, it is possible to reuse existing instances of data types in the same type class instance as well. And we'll also reuse the constraints in the instance declaration for that. Okay, so let's show what it's trying to explain. This gives us the ability to specify the instance for polymorphic data types with some conditions or constraints. Just show us. Let's see it in the example of the archenemy type class instance for the maybe something data type. So archenemy A, so that's a constraint. So we've got an instance and that constraint is of archenemy A, and we've got an archenemy and the maybe of archenemy A. Okay, so it's kind of like we've got an archenemy inside of archenemy. That's what we're trying to do here. So we're basically trying to do a maybe instance, but with the A, we want that A to actually be of the class, the type class archenemy. So if you look, this is obviously our method, which we remember, and our method would be a maybe A to string. So we know when we declared the class, it's A to string. So here it'd be like maybe A to string. And we know that A is actually of the type archenemy, so that's going to get interesting. So how do we act with just? Well, with just, we literally just want, because here it needs to return a string, so we're going to have to call archenemy on that to get that value. And because we know archenemy takes a value, returns us a string. So that's the only thing we can do here, and nothing. We just want to return a string, so we're just saying, oh, well, now you've given us nothing, just return this string that says this stuff. So this instance is suitable for any maybe as long as the instance of the inside type exists. You can see how we reuse the fact that the underlying type has this instance and apply this type class method to it. So we're doing this constraint. So we did it from a function point of view, which was here. So we did some constraints there, and then you can also use a similar constraints when you create these instances. I don't know. I mean, yeah. If anyone has any questions, you know, whether it be here or on YouTube, please ask, because I don't know. Maybe I'm going a little bit too fast, and if you're a newcomer to this, especially if it's your first go, it might be a little bit. See, the problem I find with Haskell, the sort of underlying problem is all this stuff, you know. It's super terse, yes, it's the terminology, and you can't get it wrong. When someone's explained something in Haskell, they're not going to get it wrong. But when you're a newcomer, you're kind of like, the fuck? What do you mean? I don't know. But when you hear me sort of explain what's actually going on, it definitely makes sense. You can understand that there's some sort of a constraint. And we're saying whatever we pass to maybe here is going to be of the archenemy type class. Yeah. Okay, I'll keep going. So often we've gone. Okay, task 7. Often we want to compile several. Oh. Okay. So for me, type classes were weird at first because I have strong OOP background. And the same, yeah, that's once, yeah. It's kind of, I mean, it's not, yeah, from OOP, I guess it's not too dissimilar. It's got way more flexibility, isn't it? Because in OOP, it's a very much a parent-child relationship, isn't it? That's kind of how you end up building these things that all live under this specific class. But here, it's literally just a template. It's just saying, I've got this thing at a very top level. You know, you can just do whatever. Oh, excuse me. What time is it? Oh, have I got enough time to do this? How many is it? Maybe I'll see if I've got enough time. So I should probably be stopping. I'm getting hungry. It's hungry time. Often we want to combine several values. Okay, so often we want to combine several values of a type and get a single value of the exact same type. Okay, we can combine different things: treasures, adventures, groups, heroes, etc. Yep. So it makes sense to implement a type class for such a concept and define helpful instances. So this is, you know, essentially append. If you've not seen it before, it's the ability to put two things together. So when you use append in strings, you know, so that'd be the, you know, so you're the old classic hello world. Okay, so that would return, obviously. Whoops. Whoa. Yeah. Okay, that would return that. So, but there'll be somewhere, because we're both using append, which is that, and string. There'll be a type, an instance for append string. This is what it's doing. Actually, let's just make that, because append string, for example, where append, and it'd be an A and a B, so we'd have a string A, string B. Actually, it's not going to work for string. Well, it will, but it's not. It'd be plus plus. Yeah, it's not going to. You can't. Oh, okay. Let's give it. What does it want us to do? Maybe. I guess it's with maybe, isn't it? Okay, that's cool. Let's do that. That's fine. What's wrong? Expecting one more argument. Append A. Oh. Let me see. Append. You can find definition. Okay. Blah, 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 blah. Okay. We will call such a type class append. You can find its definition below. Implement an instance of append for the following types: the gold new type, where append is the addition. So is gold going to be an integer, I guess? Data. No, new type. New type. Gold. Gold is an int. Okay, that makes sense. Whoa. So append, instance append. Oh, whoa. What am I doing here? Yes, I guess it'll want some of this. Wow, hello. What should we make it of? No. Oh, I'm a bit. I don't think it. Let me just try something. Why is it not? Yeah, I thought it was. But we don't want to start putting flexible. But append takes an A. This is like the confusing thing. Instance. Well, or instance maybe. Yeah, but then we're missing. Oh, you mean just keep it as A? Yeah, I'm not. I mean, we'd have to have. Yeah, okay, there we go. You're right. Sorry. Yeah. So we just want. We don't care what that is for now. We just want it to be A. Which makes sense, except we're not telling it what A is. So the gold new type where append is the addition. So here it'd have to be gold. Gold would have to be gold A, I guess. Which is int? No, no, no. It wants maybe int. That's annoying. Let's try just adding that for a moment. Okay, it's happy. Okay, here. So what have we got? We want a maybe. Okay. So yes, we've got A and a B. So let's say if any of them is nothing, it doesn't really matter, does it? So if either is nothing, we should probably make the nothing class last, but it's whatever. Okay, so that's nothing, and then append of nothing, then that's also nothing. Okay, so we've done that case. We know what we're going to return. Append, and then here we'd have so it'd be a just of A and a just of B. Okay, so we've got A, B, and then if we look, actually let's just have a look. Errors, here we go. Come down a little bit. So what have we got available? We've got B that's a gold, A that's a gold. Okay, so we need to grab those values out. So we could either, we can do it here. Let's do that. Except it's not going to work like that. It's definitely not going to work like that. It's not going to work with whatever I've just done. Yeah, here we go. So we're grabbing the values out now, out of gold. Okay, so now we've got A and a B. So if we look at what A is an int, B is an int. So we know that we've grabbed the values out, so they're ints now. And then we want to use it, so we want to do, literally, we're appending them. Oh no! Maybe gold. Oh yeah. Hold on. Look at the return. The return type. It wants a maybe of gold. So here we obviously want a just of something, don't we? Because that's the maybe. Because we've passed everything else. If it's a nothing, you know, we'll return nothing. But here we definitely want a just of something. And then in here it's saying it needs to be a gold. So at this point, we've got to wrap things back up basically. And then here we want that to be an int. Yeah, type holes. Literally, look, I've just made this function by just following, going, okay, well, B's an int. So we've gone from like this. Right, found a hole, maybe gold. Okay, we've done the nothings of maybe. We know that maybe's got a just and nothing. So let's make it a just. Obviously, it's going to potentially be more than one value. Let's go. Next, found type hole. It's a gold. Okay, cool. So let's do gold. Let's find out. Now it's the next value needs to be an integer. And what have we got? We've got B that's an integer and A's an integer. Okay, well, let's just do A plus B. We're happy. Happy as Larry. And then when we want to use it, so wherever we use maybe, yeah, literally wherever we try and append maybe gold. So whenever we use it, so say we were to use it somewhere, let's do it. Funcs. We're going to give it a maybe gold. Is that what we're going to do? Yes. And we're going to return. Should we take 2 maybe golds? Yeah, let's do that. And we'll return a maybe gold. Maybe gold. Which is essentially... Anyway, let's just do it. We'll create a function that can do what's happening. Yeah, okay. Let's do it. Because this is what we'd need, ultimately. Append funcs. Okay. And that'd be... let's just do... Because if they're both... We have to do a little bit more pattern matching. Should we do it on the exterior? Yeah, let's do it on the exterior. We can do the same. So that would equal, oh, nothing. Pen funcs, that, whoops. Yeah, I'm literally just writing append, aren't I? You're totally right. What am I doing? Oh, help me. Well, I was going to... no. I was going somewhere. Look. There is. I was going to do this. There you go. I just wanted like a quick demonstration. So now we could use the append function, and we know because that's a maybe gold and that's a maybe gold, it will return us a maybe gold. So yeah, you're right. But at the same time, that's it in use. Ultimately I am writing append, but I've just inlined it in here. Which is a total waste of time. What was the other stuff? List. Where append is a list concatenation. Oh, okay. Should we do it with that then? Okay. The instance for maybe A. So you think what? Rather than have gold, just do it maybe A. Is that what this one is here? Challenge. Maybe where append is appending a value inside just constructor hello world equals hello world. Yeah. But they... Okay, so if any of them can be. It depends. I mean, here it looks like it's... Because it is part of the list, I guess. Let's have a look. Yeah, but then that looks like it... You know, what are we making the A polymorphic? Because here it's clearly... Because we can't just make it an A, because we can't just append A. Because, we don't know if the inside of that A, is it going to be a string? Is it going to be an int? Is it going to be... Do you know what I mean? We'd have to, like... Yeah, we'd have to... Well, we'd have to make loads of different instances. We'd have to do instances. So say we were to say A. Yeah, we'd have to like make, and then we'd have to constrain it to num or something like that. Obviously it's not going to work now, but yeah. You can't general, but if there's an... But that's how they get around it, I think. You'd still have to give it to another class. A num, and then num would take all of... you can't just make something up, basically. So you're right. Have I just broken that? Yeah, I have. That was gold. Gold! Going for gold. Okay. We'll just do the list one and then I'm going to stop, I think. So, instance. Append. And what we're having... where? That can't be right. Hold on, let's find out. Append. I mean, have I got to do it both way or? Oh, I'm gonna have to do loads. Yeah, that's fine. No, why are you happy? Clearly, I've done things wrong. Yeah, I thought I would. But you can't do it just to that. It'd have to be... The one you see it normally is to list. Which makes sense then. Yeah, it'd have to be to list. Okay, so we do it like that. Let me think about this quickly. Yeah, we can do A. And then append an empty list of B. Oh, BG. Is B? That makes sense. Okay, list is not going to be happy. Yeah, of course it's not. No type constructor. That's not going to work either. well, it will work, but that's not what they want. Clearly not what they want. Now we're going into data kinds territory, which is not what we're meant to be doing. Yeah, that's fine. Add data kind extension. Yeah, let's not do that. It's list. Oh no, it is for list. Okay. Okay. Right. So I'm using the wrong stuff. It's fine then. I need to... Come on, you can do it. Compile. Show me my error. List is not available. Should we import it? Or should we just quickly make it? Let's just make it. Okay. I think it's saying it has it from import chapter 4. Should we just do that? Oh, it's in chapter... Hold on. We're here. Oh no, we're in chapter 3. Okay. Yeah, let's just do it. Let's just import it from chapter 4. If they've got their own. Has it done it? Expecting one more argument to list. Yeah, okay, that's fine. So I keep forgetting. I keep thinking of functors because with functors you ignore the... so what? I guess I called it empty something? Oh, we're going to have to look at... Go to definition. No? See definition, CD. There it is. So we've got empty and cons. Okay. So append empty. No. Empty and A. Turn A, and then let's do B. Well, I should call that A as well. Ooh, why have you given it? Let's have a look. Empty is no value. Yeah, that's fine. So we're expecting 2 values. An empty. Oh. Let's do this. Let's just do this. It'll be quicker. Because we're going to run into a whole world of pain. There we go. We'll just do a bit of that. And then it'll be happy. Alright, save. There we go. It's happy, and that should be an A as well. Okay, so we're saying we can't append, and you know, if we are trying to append an empty list to A, well then just return A. And if we're trying to append A to an empty list, then again just return A. And then if we're trying to append cons of A, put that there, and cons of sugar. Alright, is it going to be AB? CD. Yes. Type holes. Here we go. So it wants to return a list. So now we need to append them. So where are we going to go? We're going to go... So we want to type hole for list A. So the first value would be A plus B. And the second value would be append... no, why A, B? It'd be A and C, because they're the first values. Hold on, let's just... I've totally confused it, haven't I? A and A's, B's and B's. That makes more sense, doesn't it? And it'd be A's and B's. There we go. So, oh, hold on. I didn't see your messages. Sorry, Leo. Because with the standard list, it could be an instance append A where, yeah, well, yeah, it's a bit No, because I think so. I'm not sure. But in this scenario, I can explain this. So yeah, so we've done the empty ones, and now we've got the cons. So we know when we do a cons of something, we get the head, and then the rest of the list. So if we look at the type, that's still a list of A, and that one will just be A. So we're grabbing the very first value of the list. And same, we've got our second list. Okay, so if we want to append those, well, let's just add both of those first values and put it back in a cons. So we've got both of those first values. Yeah, that's fine. But now we want to, the second value has to be the rest of the list. Well, we don't know what the rest of the list, we can't append them. So we recursively call append, and it will just do it like a recursion. It will just keep going around. And then once it gets to empty, it will just return us the A's. So yeah. And then this will like make up this big computation of A plus C, A plus C, A plus C, blah, 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 and then we'll get the result. A plus, oh, of course it's not. It should be A plus B. Don't know why it didn't. And that should be a tick. And, oh, but, I've not given it a constraint. Should we say it's a num? Because I guess we don't know, so we have to tell it that it's something, because it can't just guess. Yeah, so A has to be some sort of a constraint, I'd assume, because otherwise, I mean, what? Otherwise it'd be that's just gonna no. We'd have to give it a constraint. It can't, it can't tell how it's going to append these two things. Okay, I can explain. So what's happening is we're saying A can be absolutely anything, okay? But the way that append works over lists... Let's have a look. Let's have a look. I'm going to see quickly. I see what you're saying though. I get you. So you're saying, couldn't you just concat both lists without changing the elements of the list? Yes, but I don't think that the idea of that was that. So let's have a look. Because I mean, I think, they'd probably mean append like this. Oh, so what, you'd think it'd potentially be more on this vibe then? Yeah. So then we wouldn't be restricting it to num class. Then it's still not happy because... Yeah, it's much like we can't... we have to give it some sort of a... We have to give A some sort of a constraint. Whoops. Whoops. Do you see what I mean? So whatever we're going to use here, so if it's plus plus, like you were saying, for example, then it'd have to be of, what would a constraint be? Could match expected type, the actual type A. So it wants to be, so you'd have to give it a constraint of, I can't remember where, plus plus, plus plus, for all A, append two lists. So it'd have to be, what would you have to, I'm not sure. I'm not sure you can leave that polymorphic without telling it some sort of constraint to the A to tell. Instance A where append equals plus append A. Oh, so you're trying to go... Oh, we've used... Yeah. No, that's perfectly fine. But we're trying to do it over the list, this data type, rather than so. But then, because you use a plus plus, see, it's already got this underlying implementation. So that, see how it takes a list and a list and then returns a list. But if we use ++ here, we don't have that implementation exposed to this list. So that's why here I'm having to tell it what the contents of that list are going to be. So that's why that works. That's why if I change that to int, then this works. You know, you're just trying to determine how you want to make your append be. But if so say, let's go back to semi-groups, for example, and we're going to do that instead. Then we're doing something similar. Yeah. I don't know, let me know. Is that super confusing? I can see the way you've done it, and that's perfectly fine. Definitely. If you know, if we don't use list and we do a list of A, sorry, so if we were to replace that with like that, then yeah, I can see, well, obviously all my stuff's going to be, you know, I'd have to, hold on, let's just quickly, let's do it the way you did it and see if I'll try and do it the way you did it and see if it's what I'd do would be the same as you, and then we'll find out, won't we? So that'd be A. That we don't care. Append. Okay, so for some reason it should definitely be not happy, but it seems okay. Go do your stuff. Go do your stuff. Oh my god, I'm gonna have to stop. I'll get this though. Cool, you're just happy. Why? I don't know. Why are you happy? So look, where A. Well, I mean, this should definitely be that. Okay, that's better. That was a bit weird, wasn't it? That's happy, and then this stuff's not going to be happy. So here we're going to have we have to do it like this, which is again very similar. Well, actually, we'll put them together, and then because you know we just had a type variation of it, and then at this point, we could use ++ on that one, and then here we'd have to return the append A of S, and then we'd have to cons there. Oh, so is it A is expecting what is it, just one value? Okay. Let's look what type holes. It wants a type hole of A. Let's just quickly go here. What do we have available? Like this. Hold on, I'm just going to look. I'm going to see if I do what you do. So we've got A, B, and A. So it can only return one or the other, which is not what we want. Oh, I guess the other solution would be, which is terrible. So look what you did. I got a pretty good feeling. Oh, yeah. Totally. Yeah, you can do that. Oh, so you're just taking the very first value. And then you're not caring about anything about this. Cons, A's and B's. Append A's. So your append though is only ever going to go over, you know, it's going to cons the A. When does it get to take out values out of B? Because you expect it to sort of do one and the other, wouldn't you? You'd expect sort of, if you have a list of, you know, 1, 2, 3. Let's say we want, okay, and we want to append 1, 2, 3. So, well, the functionality. Hold on a second. I'm getting real lost. append. Okay, where's byte string? What is byte string? We don't technically. So we go text. Text. So we go source. Append. Oh yeah, so it's literally like that. Okay, that's fine. Yeah. See, within. Hello, go back. Within here, append. So yeah, so we're literally trying to do that, which entails should return us. Yeah, so let's have a look at what yours does. So cons A. So we've got that, and then we'd cons A onto the append of A's. So we'd have the 1 there, yes, and then the 2, yes. Yes. You're right. No, you're totally right. Yeah, so you just at each level that'd do 1, 2, and then 3. So, but it's doing that again and again. So ultimately, you know, you'd end up with a thing sort of like that, and then inside of here you'd have like a, you know, let's imagine that's like 1, and then here that'd be 2. I'm creating too many of these, but yeah, and then it'd get to 3. Yeah, so that's the idea. Yeah, you're right. Yeah, so it'd do all of those. But oh, let me think though. So say we go through, we do 1, 2, 3. Okay, so that makes sense. That creates that. So, but then it'd hit empty on there, and it'd return us the result of a const onto this list. Yeah, no, you're right. Yeah, that would work. Totally work. Because essentially, when this is empty, it should be there. Then we return whatever is built up on the right hand side. I think that's right. Yeah. What I'll do is I'll look into it because I've really got to finish, and yeah, I'll look into it and I'll get back. I'm pretty sure that's right, because if we look, I mean, let's have a look at the where's append then? Append here. Works, yeah, with text it works quite differently. Byte string might be a little bit nicer. I think I actually worked on a byte string one, to be honest. Don't press that one. There it is. Oh, it's map end. Great. Oh yeah, okay, hold on. And your maybe, let me see. So just append A2. Okay, so hold on. So you've given it the type constraint of append A, MA nothing, nothing, MA. Shouldn't those return nothing though? Because when you try and let's have a look. Let me have a look. I could be wrong. I could be wrong though. Just bear with me. No, just go. Just open it. So we want to. What happens then? Just one. This isn't going to work. This isn't going to work. Yeah. Of course it's not going to work. No, because now we're like in the apply environment. You know, we can't. Well, first and foremost, there isn't an append for. Yeah. I don't know. I think it's a little bit. They've basically confused it a little bit. I don't know. I don't think the examples. It's opened up for all sorts. Because technically, to append a maybe and a maybe, you have to get to the internal values. You know, look, we can't. Whatever we do, you know. So say we want to do just one. Well, plus just two, for example. It's just not going to work because we're missing. This is when you were it won't be in this, but it's when you start using things like that, applicative. So ultimately, you end up going, you know, you have to get. You can't do any sort of appends against a just value. You have to get the value out of it. But saying that, that's kind of. I mean, you do get the values out, but I don't know if recalling append would. Should we try it? Let's try it. There. Append maybe. So I did. Oh, because we got a bunch of stuff that. There. This doesn't work anymore. Cool. So it seems happy now. Let's try and use it, shall we? So technically we should be able to use that. So let's go there. Let's what am I doing? Go there. Let's reload that, and let's load. What chapter? We're chapter 4, aren't we? No, 3. Yes. And then do we have append? Yes, we do. So let's do just one append. And actually, I'll just in case. Oh, I need to put append first anyway. How is it? Good effort. Then you are the winner. Non-type variable argument constraint append maybe use flexible context to permit this. Yeah, just check the semi-group instance for maybe, and there it's like what I did. Oh, but it didn't give any constraints over here. Surely it must have added another one, because at that point it should have added semi-group. So A needs to be a semi-group, I'd imagine. Because right now, look, I've tried to do just one, but then it's saying, well, first and foremost, it wants flexible context. So let's say set, what is it? I forgot how you set things in here. Is it X? No. X? Yeah, there we go. Okay. So let's copy that. See what errors we get now. Yeah, append just one. Oh, first and foremost. Yeah, so no instance for append integer. Okay, so we'd have to write a. Yeah, so I think, I don't know. I thought that here we'd have to sort of go. Like that. Whoa, hello. And then we'd have to. Like that. What are you on about, Sam? What is it? Sam class. Oh, yeah, of course I don't want Sam, I want a num. Redundant constraint, num A. Oh, it's redundant. I don't know then. Now it's not. Now it is. I haven't got a clue. I'm going to have to look at it and see what's going on. But still, go away. This stuff shouldn't really be at beginner. It's cool to look into it. It's cool for us. But, if you just started off, maybe not. Yeah, I'm going to have to look into that and then get back on the next stream, which I'm going to end now because I've lost my thing where I need to shut it off. Here it is. Woo, woo. I'll do a bit of this before. Yeah, this is us right now trying to work out what's going on. Was there? There's answers though, isn't there? Quickly, actually, let's have a look what the answer they gave. There's a solutions. Wasn't there? Chapter 3, solutions, chapter 3. Yeah, no worries, but I'm going to look at this. Chapter 3. Where is it? Further down, further down, further down. Book titles, we did that. Magic, we did that. House, we did that. Health, we did that. It's the next one, isn't it? Treasure chest, blah, 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 blah. Here we go. Exactly the same as you. No. Yeah, it is. Bizarre. Well, you're the winner. Yeah, you're right. So I guess if you try and append nothing with MX, of course you're not going to get nothing. You just want to return. There's nothing to append to it. But then, so yeah, that's the one that would have caught me, right there. Oh, okay, and this, right? Okay, well, yeah, I guess so. So it wasn't over list at all. But then it says, do you mean that kind of like makes it look like used the list? But yeah, it wasn't. Oh well, yeah. Well, no worries. Thanks for joining in. I shall do another stream at some point soon. Probably same time, I reckon. Maybe tomorrow. If we get lucky. What time? No, it won't be tomorrow. I think I've got an interview tomorrow at that time. So it might be later, or it might be the day after. Well, I'm Vince. Cool. All right. Well, take care. See everyone soon.